how to use Bash for multiprocessing because it's interesting for as a starting point. How to use Python processing, Dask, and that's everything. Okay. I have also into the upper folder an example folder with few files to understand and start practicing. Okay, so MPI, OpenMP, Python parallel is Dask and multiprocessing and few script to start learning. Okay, so that's if we have time today, we can do it during the workshop, or you can do it later and reach me on my email. It's okay for me, no problem. So let's start with Python parallel programming. If it lets me click here. No, I cannot. Oh, nice. So again, the Chris Woods website have tons of things of that with example, step-by-step introduction. So again, if you want to go that way, it's very, very well made. Okay. So parallel programming with Python is functional based. Okay, so performances are limited if you use raw Python because it's not. I mean, Python is interpreted on the fly, so it's not like a binary. Okay, so most of the time you are going to import binary-based library, so mostly NumPy or Panda, to do calculation. And calculation can be done locally or on a cluster. It's up to you. So again, I'm sorry for that. It's like with hardware for parallel computing, we have some mandatory knowledge to cover first. So few Python fundamentals. So Python natively uses something called the GIL, Global Interpreter Lock. Okay, so because it was at the very beginning made on the assumption to be a serial script. So the multi-threading is not very well handled. You need to go with multi-process, okay, even if it means distributing the memory, but you will see that Python will handle that for us. So we need to go with something called multiprocessing, okay, to solve the GIL issue. It has some overhead because we are going to spawn processes and we have some memory communication, but you don't have to handle that. Python multiprocessing handles it for you. Okay, so basically, the difficulty with the GIL is that when you do multithreading into Python, each time a GIL do some I/O, memory, disk, whatever, everything is locked until it do what's needed. So you have some kind of lock all the time, so it's absolutely not efficient. If you want to learn more about the GIL, there is some nice website here. Again, don't bother copying right now. You will have the slide at the end. So in Python, every function is an object, okay? So you can use it as a variable. So it's called code as a function, okay, as a type. So if I create a function called add, okay, just return a plus b, sorry. If I just say, okay, I want to print add 6, okay, it will print, but I can also say, okay, a equal add, so I'm going to, a is going to be a function, and I can print the result of a 6, 4, and I will still get 10. Okay, so a function is an object you can manipulate. Also, you can get a lot of data on the function of the object itself. Okay, you can access a lot of things. So if you create a function like that, you can, okay, I want to print the name, so you can get the name, because if I created it another way, if I say, okay, a equal add, then the name don't change, and I can print the documentation or, you know, a lot of other things if you need it. Once you created a function, you can use it, it can be used as argument to other function if you want, okay? So if I create add here and call function here, which doesn't make really sense, but we don't care. If I call call function with add, the function is passed here, so add goes through here and is calculated here. So it can be used as an argument, okay? So don't be surprised later when we pass functions as arguments when doing parallel. It's feasible. Um, Also, well, you can see that I can call the function name argument inside the well, the function still have, when you pass it as argument, you still have the different parameters available. And well, the same apply here. You can create a call function and call multiple things the same way it will always work. So that's an example. Okay. So now if I want to apply the same function to a set of data. So let's say I have two arrays of data. Okay. So it's called list. And I want to sum all items one by one to create a third array. So it's A for each index plus B of the same index equals C of this index. Okay. So to do that, we could create a for loop, okay, and append it to C. So we create a zip of A and B and do the add on each element. It's possible, okay. So we will get the result, but instead of doing that, we can, well, we could create a mapping function, but it's not very interesting. So you can use what is called map in Python, okay. So it will replace a mapping function. So a map is an object called an iterator. So if I say result equal map multiply A and B, okay, so remember multiply was that function. I multiply my two items and return the result. If I have A and B that way, to list, to be hide. If I say, okay, I want the result, so a list, to be a map of multiply A and B, you can call it this way. And it's going to iteratively calculate the output. So it's going to apply the mul function on all items of A and B. But you have to understand that an iterator is waiting to be calculated. When you do that, nothing happened because I am not using the output. So it's called lazy evaluation. You have to remember that later, okay, for later. When you deal with parallel calculation, we are going to do that a lot. We kind of submit a task, but it hasn't been executed, or it's currently executed and you will get the result later. Okay, so it's called lazily submitting the things. Okay, so calculation still hasn't occurred. So if I print result right now, I just have a map, okay? And if I ask for the result to be printed, then it does the calculation and I see the result. Okay, so it's an object. Also, another thing interesting is that sometimes you want to do a map, but then I want to calculate the sum of all of that. So again, I could do a for loop, but I can also use a reduce. Okay, so it can be a sum, a min, a max, whatever, on an array of data. I can do a reduce. So let's say I did my map for the result. So instead of doing a loop like that, I can import reduce and okay, I want the total to be equal to reduce add on the result. Okay, I don't know if you see with that here. And total is calculated this way. So what I am interested in map and reduce because it's used later in parallel computing. So you must note that you must provide two arguments for a function to be reduced. Okay, so the function to be result and a result itself. Okay, that's that. Okay, so let's start with Python synchronous parallel processing. So Python library we're going to use, and the most well-known is called multiprocessing. So that's a very good way to start parallel on local system. It's pretty simple. Of course, you can do extremely advanced things, but when you start and do simple things, it's pretty simple. So you just have to import multiprocessing. You have an help available. And if you print multiprocessing.cpu count, it say, hey, on your local system, this is the number of cores available. So if you have a 4-core CPU, you will see 4, etc., etc. Okay. So basically, when you you use multiprocessing, you are going to create a pool of workers. Okay, so it's called workers. You are going to create a pool with the number of, so you can ask for a specific set of workers, or you can let multiprocessing just use the available number of cores to generate the number of workers. A pool is an ephemeral item. Okay, it's just here during the calculation you need, and then you close it when you don't need all these workers anymore. Again, remember, these workers are going to, each one is going to use one of your cores on your CPU. So it will distribute the load. So be extremely careful right now. When you do multiprocessing, your code must be strictly structured because each fork, this is processing, it's not threading here. Even if it looks like threading, it's processing. Remember, because of the GIL of Python, we need to use process instead of thread. Even if it's handled by Python like kind of threading, it's multiprocessing. So each fork will run its own copy of the code. So you have to be extremely careful. You have to structure your code. The import should be at top of the file. The function should be defined at top of the file after the import. And your main code should be protected by the standard if name equal main, okay, statement. Because if you don't do that, it's going to be a huge mess. So from now, with multiprocessing, you cannot really anymore do some kind of interactive Python. You can, it's kind of difficult. Now, better way is to create file and execute them. Okay. So this is an example here. Remember, we have our function add on minval. Okay, and this is how I will structure it before I start with multiprocessing. My import, my function, and my main execution here under if name equal main. Okay, so this should be structured this way to avoid any issues. Sorry. Okay, so if we want to do parallel calculation, we create a pool of worker and we discard it later. If I have a 2-core CPU, if I print the number of core, I will see 2 cores. Okay, so it will go this way, just create 2 cores. If I have a 4-core CPU, I will get 4 as CPU count. Again, you can choose more or less if you want to overload or don't use all the cores. So here is an example. You can do a request on a map calculation to use the pool just allocated. So let's say I have a function square. It's square? Yeah, or I don't remember. It shouldn't be square. I think I made a mistake. Anyway, it returns a multiplied by its himself. Okay. I think it's not a good term. Anyway, so I create a pool. Okay, with a number of cores available. I create a range. This is my data. It's a list. And I do the pool.map, and I want to execute this function on this pool of data, this set of data. And this is going to be executed on my pool of workers. So we can create a dedicated print to see exactly what's happening. Okay, it's when you start playing with parallel, you should abuse the PID things here to display which PID or PID. Remember, a PID is a number allocated by the system to each process or thread. Okay, so remember that. So you can print the PID and see what's happening. So here I added a print into my square function and say, okay, I want to just show who I am. Okay, so I execute my pool like I just showed before on the range of 1 to 6 and with square. And if I execute that on my 2-core CPU, Python 3 and the name, you can see that I have 5, because remember, 1 to 6, it's 5 data, 5, okay? If I execute that on my system, I can see that one of the worker took 3 calculation, 1, 3, and 4, and the other one 2 only, 2 and 5. So basically, we can think that this one got this item, this one got the item, they both did that together, and then they try to pick up each item. So if I print that over the time, I have my main process here that created few workers, and they communicate together. First, they were allocated 1 or 2, so each worker did a small task and then come back to main process and say, hey, I've finished, I want another task. So another task was provided, so both of them did another part, okay, and then since we only have one remaining item, the main thread, the main process say, hey, I don't have any job for you, but for you I still have one left, so do it. It's probably because that one went first back and say, hey, I have another job. It was first before that one. And it has the last task to do, and when it's done, finished. You see what I mean? So pretty simple. So pool.map is limited to a single argument. Okay, if you need to provide more argument, you can use star map, pool.starmap. Okay, but it expects a list of tuple. A tuple is kind of a chunk of data. Okay, you cannot just say, okay, I want to provide A, B, C, etc. to do my calculation. You need to zip them. A zip is a list of chunk of data to be performed together. So right now, if my add function need two arguments, one item A and one item B, these are my two arguments to be passed to each function. So these are chunk of data. This is called a tuple. Okay, we just use zip to all our arrays to zip them into a single huge list of tuple. Okay, so this is another example. I want to add A and B. So remember, before we had only one item. Now we have two items, A and B. So I create my pool with 4 workers. I ask 4 workers explicitly here. I have A and B. And I am going to create a list of chunks, so a zip, a tuple. You can see here I created a tuple of data. So this is A1, B1, then A2, B2, etc. together. And I pass that to my add function with a star map, and I get the result. And you can see each worker got an item to do, because I printed here. Each worker got a task. So the 4 workers performed in parallel together the calculation. Of course, remember, these are examples. I mean, to do such calculation, it would be stupid to use parallel. But imagine you have very, very large arrays. It takes a lot of time with one worker, one in serial. Then, in that case, distributing the load of a lot of workers means using all the cores, so it would be efficient. Do you have any question on that part before I go further? So again, don't worry, you will have the slide and you have the tutorial online with examples.
Any question? Okay, you can continue.
Okay.
Okay, hold on,
So
there's a question. There's a question.
Yes, of course. Of course.
My question is, in parallel Python, how can we indicate the number of core or the number of thread we want to create?
Here, you see my screen? When you create your pool, you specify the number of workers. Here, I said I want to use 4 workers. Okay, so I can see that here. If you don't know the exact number of workers on your current system and you want to use the whole available cores, you can use, where is it? Sorry, this CPU count. This function for multiprocessing automatically detects the number of cores available and will create a pool of this size.
No, I know. With that instruction, you can use directly all the number of cores. But
Yeah.
for example, when I have 8 core in my laptop, and for a task, I do not like to use all the whole 8 cores, but just 4 cores. how can I indicate that
Here,
for the program
like
to
that,
use only 4 core?
here, that way. You can hard code it when you create your pool. Here, I ask for 4 cores. You see what I mean?
Okay, okay, so, okay, yes,
It can be a variable.
okay.
You can, for example, implement some
Thanks a lot.
instruction to pass something to your code. Yeah, you're welcome. No, don't worry. I mean, it could be, I could use, for example, in Python, you can read current environment, current variable environment. You can just say, okay, I want to export a number of core and then read it and just inject it here. There are a lot of ways to configure the number of core you want to use. Any other question?
Stone? Okay, you can continue.
Okay. So now let's go with asynchronous parallel processing. So that was this, I would say that would be the first step. First, try with that. That's more than enough to start. Then, if you want to go further, let's try with asynchronous parallel processing. So you can assign different tasks to worker of a pool. Just one item. Remember, you can create multiple pools. So you can play with that too. You can create 2 pools of one with 6 workers, another one with 2 workers. If you have an 8 cores system and you want to manage, it's up to you. Okay, remember that. Then, if you want to apply some calculation to some workers, you can use the apply function. Okay, so right now in this example, I created a fake long calculation with a sleep function. So it takes a specific number of time. Okay, so this is a fake, a purely fake calculation. And if I ask my pool, so I created a pool of 4 workers, and if I apply, so submit it to my pool, you can see it took 5 seconds. Okay, and if I do the same, if I apply it to my pool another time, it's going to take 10 seconds, because that one is a blockant item. So it waits for it to finish and go to the other one. So it took 4 seconds. And this is kind of stupid because I have 4 workers available. And here I submit a single task. So only one worker is going to work and the other one are going to wait for it to finish. And then only one again will do the second step. So this is stupid. Okay, so sync is okay if you have a massive task, okay? Uh, when you have something that you can feed your core with a lot of tasks, and it's okay. But when you have a lot of tasks to execute and you don't really know how much time it's going to take for each one, it happens when you do statistics or things like that. You know, when you look, when you scan a range of data for a specific set, sometimes you find it very quick, so it will come back quick. Sometimes it takes more time, so it really depends. So by default, every operation you do, map, apply, etc., are blocking tasks. Okay, so they lock the execution. You can play with asynchronous. So if I again do the same thing, but this time I ask for an asynchronous execution, it will take 5 seconds. Okay, remember, you can see here that both two workers did the calculation in parallel, and basically that part was in synchronous, and I waited here for them to finish. Okay, so this is in synchronous. I just submit task and wait for them to finish later. So this is where asynchronous calls are efficient, and this introduces the notion of futures. Okay, so futures are lazy call. Again, you just submit something, you get a future back, and a future you can see it as an object that is the key to your future result. So you get something. It's like um, I get a ticket. Okay, so your execution say, okay, worker, this is your data I want you to calculate. do it. And the worker give you a ticket number and say, okay, this is my ticket, and when I will have finished, you can identify me. So with this ticket, you have the number. You say, hey, have you finished? No? Okay, I wait. Have you finished? Yes? Okay, perfect, nice. So these tickets allow you to identify the task in progress and ask for it later. Okay, so this is a future. So you can monitor your future. Is it finished? No. Is it finished? Yes. And futures also allows you to grab the result later. So here in this example, okay, remember I print, so I create a future, so future one, future two here, and I can wait for them to finish, but I can do something in parallel here, like an IO operation. I can write some data or whatever, or read something else for later. And once the wait has been done, so it means it's finished, these are blocked, I can print the result. So future.get. So I will see 10, 10 because, well, it's multiplied by 2 each time. So these are non-blocking calls, sorry. So I just submit something, I get a future. So this is an object, I can use it later. And I can do something else, and these are where the wait are blocking calls. So I can say, okay, now I want to wait everyone to have finished to continue. And I can use the get later to get my result. So insane function are non-blocking states. So master process is free to continue and do something else. Okay, you can also do async on map or star map or whatever. So you can just submit everything on your pool of worker, do something else, and come back later to check if it's finished or not. Okay. Do you have any question on that before we go with something a little more complex?
Okay, thank you, Benoit. It's really
Yeah.
interesting. And I was thinking, if asynchronous is going to be sequential, kind of, the core is selected sequentially. You specified the 5 cores and we're seeing result the
so
time it takes for each
you do
core
not.
to carry out the processing, right?
So
So my
you do
question
not
is,
manipulate. Yeah.
my question is, shouldn't synchronous be faster based on the fact that the processing is done the same time in parallel by the different
Mhm.
cores? But instead of asynchronous, which is done one after the other, being faster than synchronous, maybe you can shed
It
light on
depends.
it. Yes.
It depends of your for calculation.
It depends on the calculation that is being done.
Yeah,
Okay,
exactly.
okay,
Sometime,
okay.
let's, for example, if you have, yeah, as I said, if you have a massive calculation, synchronous is better because you know that you need the result of everyone and it takes a lot of time. So, okay. But sometime, for some mathematical operation, you want to submit to your pool of worker a lot of tasks and you don't really know how much time they are going to take. And sometimes asynchronous is better this way. It really depends on your needs. No question?
Another question?
Yeah?
None. Thank you.
Okay, so let's continue. So now we reach, let's say you need more power. You say, okay, I did my calculation with Python multiprocessing. It's nice, but you know, my laptop has only 4 cores. It's not very efficient. I have like 4 GB RAM. I need more. So, okay, so I need to go with distributed calculation. And for that, there are many tools, but well, I would say I would go with Dask because it's very famous, it's pretty stable, it's efficient, you have a dashboard, everything, okay? So if you need more power or you want to allocate NumPy or Panda arrays so big that they don't fit into your memory, your local memory, okay, or you need to do very intensive and complex CPU calculations that 4 core is not enough, okay? So in that case, you can use Dask. So this is an example right now of the dashboard of Dask. When you start a Dask cluster, you have a dashboard available, so you can reach it, check what's going on, etc. So that's And this is an NumPy calculation I made on my Dask, a Dask cluster, just an example. And this is all the calculation that communicated through the network. Uh, Dask handle everything for you, don't have anything to do, okay? So Dask allows to perform massive calculation on a cluster of server. It allows to distribute huge array, very big one, okay, that will not fit into a single host memory. So if I want to allocate a 10 million NumPy arrays of complex data that just don't fit into my own server, Dask is going to distribute it over multiple servers for me, and I don't have to handle it. It's just managed by Dask. That's very nice. And even that, if on my cluster I don't have enough memory, RAM memory, if I have good SSD disk on my servers, Dask is even able to swap data on them. So of course it's not as performant as RAM, but sometimes if you need to process the data so big with very efficient, today we have very efficient SSD. So sometimes it's okay to do that this way. Okay. Also an interesting thing is that Dask allows to manipulate NumPy and Panda arrays with standard command transparently. So you can connect to a Dask cluster with your Python code, allocate an insanely large Dask or NumPy array, sorry, and it will say, okay, done. But you are not managing it. It will alone distribute the array on different servers, managing it for you, etc. So that's very efficient. Okay. On your NumPy arrays, in the background, you don't see it, but it's going to be sliced into chunks of distributed data. So if you ask for a Dask array, in fact, it's a lot of small NumPy arrays distributed over all the servers. So how it works? Basically, you have your main Python code, and you are going to connect to a Dask scheduler, which is connected to Dask workers. And each worker has a lot of process workers and a lot of thread workers available to compute. So you can think that here in this example, each worker is a different server with a lot of CPU or GPU or whatever available, and they communicate through the network. Okay, so when you submit something to the scheduler, it is distributed across all workers. And remember, a Dask worker has a lot of small workers available. Okay, it's just a worker manager. It's like we have a team leader here. It's like a team leader with a lot of worker every time. So we have few team leaders, one team leader, and you communicate with the team leader to distribute to the worker. So just beware, when you go with distributed by distributed calculation, it means much bigger management time. I mean, right now we are discussing with scheduler, which discuss with worker, which discuss with their own worker. It goes through the network, blah blah blah. So it takes a lot of time. Okay, so it means you need much bigger calculation to cover the cost of discussion. I mean, of exchange or of communication. So if you do small calculation, it doesn't really worth it. If you do very complex calculation with very big chunk of data, then yeah, go for it. It's very efficient. Okay. Also, be careful if you use very small chunk of data. So something not very made for Dask, it can even become unstable. Okay, due to racing condition between the workers. So really, you need to provide it with a large amount of data that was made for it. So there are many ways to start a Dask cluster to connect to. You can create a local cluster. So from your own code, you can say, okay, I want to create a local cluster and just connect to it. So when you do that this way, it will automatically get a number of available cores and use them as worker. So that's an example here. I have a costly simulation, asleep again. It's a fake one. I create a worker here. I connect to the worker with my client. And then here I submit task lazily again. So that's some kind of feature. Remember the feature. I submit task to my cluster, and I get the result later. Okay. So that's a very simple example. And if you want to go larger, so let's say you have a cluster of servers or your small Raspberry Pi server cluster or whatever, you can go beyond and connect Dask workers to a Dask scheduler. So you have to, in a first shell, create a Dask scheduler this way. Then you have to create Dask workers on all the hosts available, and you have to say, okay, connect to my scheduler. Okay, so, well, it's mainly with IP. Basically, on my host, on my host one, I create a scheduler. On my host two, I create a worker, and I connect it via the network to the scheduler. Same here. And when I connect from my Python code to the cluster, I just say, okay, I want also to connect to that one. So everyone is managed by the Dask scheduler. Okay, so you have a lot of power available that way. Well, that slide is more when you need it. There is an easy way to launch a Dask cluster into a Slurm environment. You don't need to use complex plugin. You can play with the Slurm proc ID. So you can say, if my Slurm proc ID is 0, I want to start a scheduler, and else I want to start a worker. That's just an example. If you have the slide, so if later you face this issue, you can use that. Yeah, so you have a lot of documentation available, and if I have time at the end, I will show you a few examples live. Okay. No question on Dask so far. You have a 10-minute to Dask. It's an interesting tutorial. You can do it if you want. It's pretty simple. Remember, Dask is made for people who use a very large amount of calculation or very large amount of NumPy arrays. Any question on Dask? I will try to show you at the end live. No? Okay. So let's finish with Python with CUDA. So PYCUDA. So PYCUDA allows to use PyCUDA allows to use Python with native CUDA code.
Hello.
Yes?
Okay, I have a question about
Sure.
is it possible in Dask and in multiprocessing to declare something like what we can do in OpenMP or MPI, shared variables?
Let me compute that. Well, remember it's functional based, but can I share variable in multiprocessing? Good question. I will be honest, I don't know. I never faced that case. Most of the time, when you want to share a variable with multiprocessing or Dask, you pass it as an argument to your function call. But I never tried sharing variables this way. I don't know, to be honest. I will be honest with you, I don't know. I never had to use that. Since it's functional based, I always pass all my arguments to the function that way. So I assume all the time that functions are isolated. I don't know. Sorry for that. I don't want to lie to you.
Okay, thank you.
No other question? Okay, so let's go with CUDA. So with Python CUDA, you need to use native CUDA code. So you are going to do some C code. It's not that easy. You are going to mix, except if you do very simple mathematical calculation, then Python CUDA is going to translate it for you. But if you do some advanced CUDA calculation, then you are going to need to write it in C, the part that executes on the GPU. So the same concept apply when you use Python CUDA than when you use CUDA pure C. Okay, you have to create a kernel to be executed on the CPU. So the kernel is your function, in fact. Okay, it's just a function, but it's called the kernel here because the kernel was more an image processing term, but it was, since the GPU was made for image processing, it's still called a kernel. You have to allocate arrays on your CPU, you have to allocate arrays on your GPU, copy memory to the GPU, execute the kernel or the kernel, well, the kernel on your dataset, and get back the data. Okay. So there are multiple ways to call CUDA from PyCUDA. So let me show you all the way possible. First way is, I would call it the traditional way. You need to allocate memory, copy it, execute, and copy it back from the GPU. Remember, a GPU is a separate entity with cores and dedicated memory inside it. Okay, your CPU has its RAM memory, but your GPU has its GRAM memory also. Okay, so you need to transfer your data from your CPU memory to the GPU memory. So that's an example. You are going to import Python, CUDA, and all what is needed. Remember, you need to have CUDA, of course, installed on your local system, and you need to have your NVIDIA driver working. And we import NumPy here, so you need to allocate your NumPy array on your CPU, but you need to allocate the equivalent on your GPU. So that way, so right now, I create A, this is on my CPU, and A GPU is the same, but on my GPU. Then I need to copy A to A GPU, so this is a transfer from my CPU to my GPU, so it goes through the PCI Express link. Then I define my kernel, so what I want to effectively execute on my GPU, and this is in C. This is C code. Okay, so basically I want to execute the power, I want to multiply each item by 2 in my random array. So this is what is going to be executed. So this is my function, okay, with an argument. So again, it's functional based. Then I say, okay, now I want to execute it. Okay, so it's going to be executed on my GPU.
Dr. Benoit, just a question.
Yeah.
I noticed you didn't mention anything on GPU when you were talking about Dask. Can Dask
Yes.
also target GPU? You were primarily focusing on CPUs.
Yes, there is no reason no. I mean, you can create a Dask function that load CUDA itself. So yes, why not? Of course you can.
Okay.
I mean, it will allow you to use GPU on multiple servers.
Okay, good. Thank you.
You're welcome. No, I mean, you can mix both of them. No problem with that. Of course. So right now, I execute it on my GPU. I will speak about block grid and shell later. Okay, don't worry. And once it's executed, so remember, we have A on my CPU, A GPU. The execution of calculation were made on A GPU. You see it here. Now, I just get my memory back. So I copy A GPU to A doubled locally, okay, and I print it. I will show you that how it works. As an example, I can show you. I will do all the demo at the end. I think it would be better. So the concept is that, again, I have my CPU, I copy my data to the GPU, perform calculation, okay, and get my data back at the end into my memory, okay? So send data, send instruction, execute, get back data. A GPU has its own memory, remember that. So that was the traditional way. Now there is a faster way available, you just allocate and you use the in-out execute. So that's something provided by Python CUDA. So again, you just import everything, create your array of random elements, define your kernel to be executed, but that time I just used in-out. So that will be the whole allocating part of GPU, copy memory, get back memory. All of this is going to be handled by Python CUDA. So you just say, okay, I want this in-out, and at the out, you get the output of calculation. It's much simpler for you to handle, okay? But you still have to define your kernel, so you still need to write in C. There is an even faster and simple way to do calculation called GPU array. So that's again something managed by Python CUDA. You can create directly a GPU NumPy array and do calculation on it directly that way. So you can just bypass the whole kernel thing. It only works if you do calculation on NumPy or NumPy-like arrays, or well, I would say any kind of array, but with simple calculation. And you can say, okay, now I want to execute that simply. And Python CUDA is going to handle all of that for you. So if you want to start with Python CUDA very simply, this might be the best way. You start simple, understand the concept, and if you want to do complex calculation, you can do it later. Okay? It's the same concept. Now let's speak about these arguments. Block, grid, share. Again, these are optional. You can call the function directly. Okay? But if you want to increase performances or get the maximum output, you may need to define this value. Block, grid, and share. So let's come back a little on architecture. Remember our CPU and our GPU. The CPU has a few big cores. A GPU has a lot of small cores. And the cores of the GPU are packed into 32 cores, with each one called a multiprocessor. Okay. If I take my architecture back, you can see that here all my SM units have 32 cores packed together. And I have a lot of pack of 32 cores. Okay. And this is an example of a GPU you can find on HPC clusters. You can see the insane number of core I have available. You can do extremely massive calculation with that. So when you execute this kernel on your GPU, basically the CUDA kernel is a function, okay, as I said, that is executed on the GPU. And the parallel portion of your application, so that part, is executed a certain number of time on this same number of CUDA thread, okay? And each group of thread is called a CUDA block. And block are grouped into a grid. So I'm going to show you schema later, don't worry. So a kernel, so that kernel is executed as a grid of block of thread. And block and grid size are related to your hardware, so of the GPU you have available. So that's why I said when you don't know, you want to do a generic code, just don't set block, grid, etc. Just let the system choose for you. But if you want to get maximum performances and you know the exact hardware you will have, you can specify block, grid, and get the maximum. So this is an example. This is a CUDA thread. Okay, a CUDA thread is this. Okay, so we create a CUDA kernel, and we have a CUDA kernel. Sorry, the CUDA kernel is this. Sorry, and it is executed with a certain number of threads. Okay, so we create the number of threads is a block, and we create a grid of block that is allocated on my GPU. So we just have one thread is executed on one CUDA core. A CUDA thread block is executed on SM. Remember, SM are these, where is it? this small unit. That's an SM. A CUDA thread block is executed on one SM, and a CUDA kernel grid is executed on the whole SM available on the GPU. So on that whole stuff here. So one thread on one tiny core, one block on one SM, and one grid to distribute across the whole GPU itself. Okay, to get the maximum. So this is called occupancy, means we are going to use a maximum number of cores available on our GPU. There is a tool if you want to go and do kind of optimize to calculate occupancy. Of course, tuning this value can lead to improving performance, but to be honest, it's very complex. You need to adapt that to every GPU you have. It's not that easy to tune, so I would say just let the default value for first, and when you are satisfied with performances, when you learn everything, it's okay. When you know you want to go further, then start trying to understand how occupancy works and how to optimize that. But by default, just let the system choose for you, okay? So just remember that a GPU is a very powerful hardware. You have, remember the number of core, it's completely insane. So you can have incredible performances, but you need to feed it with a massive parallel calculation. You have some kind of ogre that wants a lot of things to it, so you have to feed it. If you don't feed it with a lot of things, it's just not worth it. Also, if your code has a lot of logic, so a lot of if or check, it will not be efficient on a GPU. A GPU is made for massively parallel calculation. But on the other hand, as I said, if you have a lot of same calculation, so it's mainly matrix operation, then the GPU are very efficient. It's because, again, GPU are made for matrix operation, because it was made for video games, image processing, or AI, artificial intelligence, which use a lot of matrix too. Okay. So that's what you need to know about GPU. So there is some documentation available, again, and now, if you don't have any question on that, I'm going to show you all of this live. Do you still have more time? Yeah, I have some time, so I'm going to show you live all of this. Do you have any question so far for all of what we have seen? That's end of slides for today, don't worry. Now I'm going to show you live and you can practice. Any question on that? No?
Hello, Benoit.
Okay.
We
Yes.
seem to be good. I don't know if anybody has have any question, so that Dr. Dam, do you have questions for him? Okay. Does anybody have questions from the colleagues here? Okay. Okay. Do you have any? Okay.
Hello, Bernard. Nice presentation.
Hello.
Please, I want to know what happens if, let's say, you have a 4-core CPU machine, and you decided to allocate maybe 5 of it to deploy a particular task. Will it work instead of 4?
Yes, yes, it will work. I mean, for example, when you start your operating system on Linux, you have tons of independent processes running together, and the Linux kernel just dispatches the load on cores. If you start, like, let's say, 8 workers on a 4 cores CPU, then approximately you will get you will have 2 workers on each core, so performances half of performances. But yes, it will work, no problem.
Okay, thank you.
Just you are not going to multiply by 8. it will still be 4.
Okay, but it will use just 4, even though you specified
Yeah,
5.
yeah. It's just that you will have two students on the same chair working together like that, but it will be okay.
Okay. I think that makes it clearer. You have just a chair and 2 students want to sit down, they can share it. Uh-huh. I think
Yeah,
that's
so
the
they can share it, but
yeah,
I
they
mean
can share it.
it's not
Okay.
very nice, but
Oh,
they can share it.
okay. I think that's a good illustration. Okay. In the absence of I don't know, comfort, you seem to have a question. Okay.
Yeah. So let me show
Okay,
you live now.
thank you.
So let's start.
Please, I just,
Oh yes,
okay. Can I speak now?
yes.
Okay, please, I
Yes,
need
yes,
a
of course.
little clarification on this. The aspect you said, if we have a lot of logic in our code, it won't fit into
Mhm.
GPU. So does that mean I need
Well,
to?
it will fit. It's just that you may not get very great performances. Okay, well, two things. First, it depends of the generation of your GPU. Okay, old GPU, you have if you check the NVIDIA documentation, you have the CUDA capabilities of each generation. Very old GPU were not really able to execute different kernel at the same time. I mean, it was everything or nothing. So when you had a lot of logic inside your kernel, it was not very performant. Today, with recent GPU, I would say it's more complex. If you don't have too much logic, then it's okay. It will work pretty well. But if in your kernel you have, I mean, it depends. If the logic is inside your kernel, it's not a very big deal. If it's outside the kernel, it might be complex. Okay, again, it's made for massively parallel operation. But if you have a small logic inside your kernel, if it's not too much, I think it's okay. Again, if calculation takes enough time, you don't care. Did I answer your question?
Yes, thank you.
Okay, you're welcome.
Any other questions? John. Okay, Benoit, you can go ahead. Okay, hold on.
Okay.
Hold on, another question.
Yeah.
Yes, thank you for the presentation. Um, I could see a lot of the concepts of what we try to emphasize when we're teaching performance evaluation generally in
Mhm.
some of our courses. And even along that line, we tend to talk about, emphasize on pipelining. We talk about the latches. And we also try to consider a situation where you have some constraint. Maybe you have written a program and then you now want a situation where you set up a constraint such that in a set of program, that job should not be shared. Such a job should not be broken for different processors to handle. Um, are you able to highlight those aspects from what you have taught us so far? Are you
So you
getting the
mean like,
question?
I'm not sure to be honest.
Pipelining,
You mean that?
pipelining, for example, latches, for example, and some setting some constraints for
Yeah,
processors, such that
I see what you mean.
yes, such that you get an improved performance on the long run.
So you mean like if you have some pipeline of tasks to do, right?
Yes,
For
exactly.
example. Okay. I would call it more well, If you have a pipeline with a single set of data, it's going to be difficult to make it parallel, okay? However, if you have a pipeline of a lot of chunk of data, let's say I have a lot of case and each one must go through a pipeline, you can use the embarrassingly parallel method, like you submit a job for each case, okay? So they will go parallel and everyone is going to be distributed and work together. You have a nice tool called Nextflow that can do that pretty easily. Or you can developing yourself, of course. Uh, but yeah, sometimes you cannot make something parallel. I mean, it's not always feasible. A pipeline is a good example. If you have a lot of constraint, it's like the Thomas algorithm for matrix. It's pure constraint. To calculate each item, you need the one from before. So it's not possible to make it parallel at all. It really depends, but sometimes you can kind of make it parallel using embarrassingly parallel method, like submitted one job for each chunk of data. An example would be, I don't know if you know Blender. It's a 3D rendering tool used to create movies, for example. By default, when you ask Blender to create a frame at a specific time, I mean, by default, when you render a movie, you do all the frame one after all. But it's embarrassingly parallel. So instead of using it as a pipeline, you can say, okay, I want each task to be the rendering of one thread. And I create an array of tasks and I submit all of them at once to the scheduler. And that's the job scheduler to manage the task later. You don't care about that. That would be one way. So the only way I think for pipeline or very constrained things are embarrassingly parallel with chunk of data. If you have only one data and everything is constrained, I guess it's not possible to make it parallel, or just make few step parallel maybe.
Okay, okay, thank you very much.
You're welcome.
Okay. Thank you very much.
Okay.
So, is
So we start with the GPU. Can I zoom? No. Yeah, I can. Okay. Can you see that screen? Yeah. Okay. Try to increase it a bit. Okay, so this is a GPU node. Okay, if I ls PCI, do we have it?
we
So
are
you
going
can
into the
see that
practical session now.
I'm just going to show few examples and then we can go to practical session. Yes.
But let me just mention that we already have your VMs. Okay, so
Yes.
and your
You
VMs
can practice.
have multi-cores. I
Yeah.
think we have like four cores for the VMs. Or
Yeah.
is it two? Okay, three. So
I just want to show you GPU because I guess you don't have GPU inside your VM. If you see what I
apparently
mean.
we don't have GPU,
Yeah.
so I think it will be good.
Yeah, that would cost a fortune, so I understand that. So right now I have a VM with one GPU attached to it. Okay, so I want just to show you Python CUDA on it, and then we can do the practical session. So here I have a VM with two cores. So I can see, well, if I do and cat and that way. So I have two cores, okay, 1, 2, we start at 0. And if I do an NVIDIA SMI, I can see that I also have a GPU available. So that's, where was it? It's a Tesla T4. So it's not a very big one. That's more than enough for testing and showing everything. Okay, so I have a Tesla T4 with 16 gigabytes of available memory inside it. okay? And if you go on the NVIDIA website, you can get the number of core, etc., etc. So if I check my, I need to, so first thing, when you execute Python CUDA, you need NVCC available, which is the CUDA native C compiler. Right now, you can see that it's not available, so I have to export my path and export my ID library path. So it means that I register to my local shell the CUDA toolkit. So the binaries and the library, then NVCC is available. You have to be sure about that. Then I can execute my demo. So I can check my simple demo. Where is it? So that's the program I showed you. Remember, with first we have the memory copy, and we execute the kernel. Then we have the in-out method to calculate. And then we have the direct method using GPU array. And if I execute that, some time to initiate, and I can see that everything worked fine on my GPU. So I can calculate everything that way. Okay. So, well, it's difficult to show you live the load because, I mean, I don't have a lot of things available right now, but basically use NVIDIA SMI command to check the GPU you have available and execute it. At the very beginning of CUDA, there was an emulator available to emulate a GPU and do calculation on a CPU, but at least to test. It's no more available. You need a real hardware now. At least you see it. So that's how you execute it, basically. Once your CUDA toolkit is linked via environment variable on Python CUDA installed, and once your NVIDIA SMI shows your device, so you check with NVIDIA SMI that everything is in order, then you can execute Python CUDA very simply, like I showed in the presentation. So now what I suggest is that you can do the practical session. I tried to make it interesting. So the concept is to show you available technologies, parallel coding, so it's parallel programming. Just don't copy paste everything on, not understanding. Okay, take your time. You can do it at home. It's synchronous. You just need a VM with, with Ubuntu, or even I was connected before. I've seen you played with Docker. Even inside a Docker Ubuntu image, it's okay. Okay, you can use it. So just try to understand how each technology works. You have OpenMP, you have MPI, and then you have, where is it? Yeah, I used GNU because it's very nice to show output input. You have Bash multiprocessing because you can even create script with multiprocessing if you want. Python multiprocessing, so I try to explain everything, and then we have Dask. And you also see this thing that is, I want you to understand. I created some kind of real-world calculation with Python. So we try to determine a prime number on a range. And you will see that the scaling is not very interesting. With serial execution, it takes 24 seconds. And with parallel execution, with 4 cores, it takes 30 seconds. So you can see the multiplier is not 4 times less, because of course scalability is not always perfect, because these are very small tasks and you spend a lot of time managing the workers. So that's an example. Okay. So if you have a question right now, I will stay available until the end of the session, and then you have my mail here. Don't hesitate to reach me. I may have like 1 or 2 day latency because I have children. So, you know, If you are a phaser, you know. Uh, but I always try to answer as possible. Okay.
Okay, thank you very much, Benoit. I don't know if we have any other
You're
question.
welcome.
Question? None. Um, we want to appreciate you for your time today, despite the short notice, and then you're able to make it for today. We appreciate you. So our next class, can we
That's
just
okay.
give him a round of applause?
You're welcome.
Thank you very much. So our next class is going to be Monday, same time.
Yeah, exactly. So
Okay.
next time we're going to see HPC cluster environment and Prometheus.
Okay. Thank you.
Sorry, I know it was a little fast with a lot of concept, but well, we have to deal with time.
It's okay. Thank
Okay.
you very much.
You're welcome.
Okay. Have a wonderful day.
Oh, thank you, you too. And if you need anything, don't hesitate to reach me. Okay. Everyone, if you want some feedback on help, don't hesitate. It's always a pleasure.
Okay. Thank you very much.
You're welcome.
Yeah. Bye bye.
Have a nice day.
And you
Bye
too.
bye.